thank you for the introduction. And I wanted to make an example to explain what is design of experiment. And since I am Italian, I'm doing an example with food. Okay. So you probably know what the design experiment is, but just to remind you, so we wanted to make an object, let's say a cake, and we want the cake to be good, and we have to choose the ingredient, the temperature of the oven, cooking time, and so we have some factor to decide. For instance, amount of sugar, number of eggs, temperature of the oven. So we needed to find the best combination of these parameters in a way we get the good taste. Okay, so this is design of experiment, just create data. Okay, create data by designing the way the parameter we change to get our test. I'm going to focus also on a problem where the goal is optimization. Okay, so I want to get a good cake. Okay. Okay, so what is intelligent design of experiment? Is design of experiment with AI. Okay. And so let me give you another motivation that is mostly main application area. That is what we call the smart manufacturing. Okay. So baking is an example of manufacturing. In manufacturing, we want to make products. And we have some machines, some raw material, we process it, we get some product, and we want to optimize this. We want to be fast, producing customized products, increase resilience, and improve sustainability. Okay, so these are our goals. And we want to find the best parameters to achieve these goals. Okay, so of course, we can use AI to do that. You saw today a lot of examples for using AI for this, even in the previous talks. But using AI in manufacturing, there is a big problem. There are some barriers, okay? And one of them is data scarcity, okay? So a lot of, in manufacturing, a lot of problems. So you think about, we want to make a cylinder, okay? Cylinder made, for instance, with metal. So we have a machine that has some parameter, it makes it, okay? And we want to learn an AI model that describe how this machine works, how the output depends on the parameter, and use this model to, for instance, make prediction or optimize it. Okay, so this is normal pipeline. Every one of us is working with this, but there is a problem that, so what if now I change context? So from this cylinder, I go to this. Okay, so I will need probably another data set because the problem is different, the response to phase is different, so I need another data set. And what about if I go from, I don't know, steel to titanium? Okay, then I need another data set. Okay, so what we are doing today is developing tens of thousands of models. Okay, we are a lot of people here, so I guess we can do it, but it's going to take time. And of course, we can do things like zero-shot learning, transfer learning, meta learning, multitask learning, but in domains that don't involve images or audio, actually for doing that, we need even more data, okay? Because we need to provide a different context, data for this, and then we can generalize, okay? So how do we do this? So actually, if you think about most of the data we collect and what is hard for AI, okay, is actually assessing quality. Okay, so if you think an object like a cake is a difficult case, so we need to define taste. Okay, how do we measure taste? We need a number to feed an algorithm to train it, and the same we can do for surface quality of an object like the one produced here. So we need images, but also collecting images in manufacturing is not that easy, because the environment is quite dirty. We need maybe to rotate a piece to see all the sides. It's a difficult automation. And then we thought, okay, but maybe we can exploit two intelligence. Okay, one is AI that is able to deal with a dimensional problem, so when we have a lot of parameters to optimize. And the other is actually us. Okay, so what we do now, we are very good in assessing quality. At the end, we are the one that buy the cake. So we know what is good and is bad. So what about using humans to do one of the difficult tasks that is assessing quality? Okay, so in a way, this way, if we can do this, we can reduce the data that we need. Okay, so, but the problem of humans that we are not good to provide numbers. We cannot say, the taste is 2.32, okay? What does it mean? But we are good at doing this, So the happy face, you saw this also, upstairs probably, in this building, this kind of happy face feedback. And the idea is, can we use this in manufacturing? What about instead of going live with a precise measurement, we go to something, maybe it's an interval that we can provide by, I don't know, looking, or maybe a ranking, stars, or even a preference. This object is better than this because it's shiny. I like it more. And so how can we use this to learn this sort of very qualitative feedback? And if we do that, we don't need probably a lot of time spending in extracting precise information. Okay, so with this, we come out with this idea where, we want to make an object, we want to manufacture something, we produce a piece, there is a person that says, okay, this is good, this is not good, this piece is better than the previous piece, and then we feed this information to an AI system that changes the recipe. Okay, we loop like that until convergence. Okay, so this means that we don't need the traditional DOE. Okay, so we just do this iteration. There is no data set. We don't need a data set to train this model in advance. We just use the data that we are looping here. It's fast and cost-effective. So it means that we can find this optimum by doing many less, let's say, experiments than with traditional design of experiment. Okay, and the nice thing that is application independent, context-free, and easy to use. So what does it mean? I can apply this idea to different domains. For instance, I can make cake. My ingredients are sugar, butter, temperature from the oven. I make 4 cakes with different recipe. Then there is a person that tests and say, A is better than C, better than D, better than B. And I use this information in my AI model to propose new recipe in a way we optimize the test. Okay, but what about drugs? So part of this in drug manufacturing is this dissolution test. Drugs must satisfy some dissolution curve, but again, the problem is similar. We have ingredients, we make objects, there is someone that assesses them, and we loop. And what about additive manufacturing? Again, the ingredient is metal powder, we have a machine, a laser machine, and so on. Okay, so this is the idea. And so it's application independent and context-free, okay? Because we don't exploit anything but data set that is built before. Okay, but how can we do this in practice? So I'm going to focus on this case. So that is one of the weakest feedback that we can provide as humans, preference. So if you say that an object A is better than B, so this is better than this, it means that in your head, there is some utility that you have in mind that says that this is, for some reason, better. Okay, for it because it is shiny. Okay, and the idea, okay, so given this preference, if we can learn the utility that you have in mind, I can maximize this utility and then understand what property of this object you have to change to make it even more shiny. Okay? How do we do this? We can use machine learning to learn utility because this is a function, and this is going to be our data set. Okay? So the idea is the following. So imagine that we want to make a cake and we want just to change the amount of sugar. The sugar goes from 10 grams to 24, just an example. And imagine that in your head, the utility for sugar is something like that. Okay, so this means you cannot even describe this. Okay, just in your head, you only know that if you put more sugar, it's good. You put a bit more, maybe it's not good, and a bit more is even better, something like that. So you cannot describe this, but it's what you feel in when you taste the cake. Okay, this is your head, and then you provide me preference. So I make a cake with 20 grams of sugar. I make another cake with 16, and you tell me that this is better than this. Okay. Then I make another cake with 20, another with 23. You say, this is better than this. Okay? And we use this preference to learn your utility. Okay? Once we have your utility, that is this blue line here, what we can do is understand what is the best amount of sugar, something that here is around 19. Okay? And then this is going to allow you to optimize the process. So we can now make the cake with 19 grams. Okay? So what is these bands here? This is an uncertainty. Because when we have not enough data, it's important to model uncertainty, because we can exploit this uncertainty to make decisions. I'm going to show this in a moment. Okay, so this is where we do what before Igor said, active learning. There is another form of active learning that is called the Bayesian optimization. So active learning is about making data sets. In Bayesian optimization, the idea we want to make data set to optimize something. Okay, how does it work? So for preference, we start with some initial preference, like a cake with 20 grams is better than one with 10. We learn a model, a utility given this few preference, like this blue line and this gray-blue area that is the uncertainty, and we decide basically which cake to do next. So in a way that you want to optimize your test, but you also to try to understand how the ingredients affect the quality of the cake. Sorry. How do we do this? By maximizing what is said to be an acquisition function, is called. So what this is a function of usually uncertainty and the mean. And the idea is, so imagine this, I've done these cakes with this amount of sugar, and this is my utility in my head. Okay, so the best cake is this one so far, because it has the highest utility. And then I think, okay, what cake should I do next to discover this, the point with highest utility? And the idea of the model is, okay, we maximize this acquisition function, and this tells us what to do next. So we're going to do a cake with amount of sugar 5, for instance. And we continue like that. Now, next time we do cake with amount of sugar minus 2 in some scale. So we keep going. And while we do that, we improve the model, and we get close to the maximum. Okay? So, and this is done only with preference. So there are no numeric data. So this here is never seen. No, we never see. This is just an example where I used to generate the data, but what we have is preference. Okay, so like this is better than this. And what we learn here, we learn something, you see, this blue function that is very different from this one, because actually many problems we don't really need to learn the true function. We just learn something that is enough to give us the maximum of the function, the optimum. It's what we do in process optimization. So we keep going, and at the end, we find the maximum. And what we do, we can also do with really few iterations. Although the function is very complex, a lot of maxima. Okay, so I want to give you, to finish, a very simple experiment. Is additive manufacturing. So probably you know what additive manufacturing is. It is metal additive manufacturing. So it's a process to make metal object, and it works like that. So you put some powder, metal powder, a layer, and then there is a laser that melts that layer. And layer by layer, layer melting, layer melting, layer melting, you build blocks. Any shape, this is just a cuboid, just for example. And our goal here is to find the optimal parameter for this machine that are the power of the laser, the scanning speed, and the etching speed, that is the distance between the lines that the laser is doing to build this block. Okay? So these are some of these parameters. And can we optimize these parameters by using preference? Okay? So what does it mean? So imagine that we make these 4 objects and differ for these 3 parameters. You see the values here. So these are our objects. And then we ask a person to say, okay, tell me what is the best object. Okay, just that. I don't want to know why. I don't want to know anything about that. So tell me about what is the best object. And the person is say, okay, in this experiment, actually, the best object is number 1. Okay, so he said that number 1 is better than 2. That I lost. Sorry, this should be 2, this should be 3. 1 is better than 3, and 1 is better than 0. Okay, so this is the example. So you can see here that actually the shiny one is this. But in terms of roughness, this is better. Okay, this is another problem with computer vision. In this case, the black sometimes doesn't really help us to understand the roughness. Okay, so this is the feedback. These are my data. So piece 1 is better than piece 2. Okay, and then we make new parameter. We print 4 blocks, and now the person says, okay, now with these new blocks, and the previous one that you said was the best so far, for me now. The best one is number 5, okay? So we keep going like that. So the first iteration, number 1, number 5, number 10, number 14, and then basically in these few iterations, we find the optimal parameters that were these, okay? So for what the person wanted to do for that piece. And we can do it with 20, 25, 34 pieces. Actually, the person was already happy with this. So we did another one just to collect data. So we did with 20 iterations, was enough for finding good quality. And then how it works. So the idea basically, we use humans, so human is just judging quality, okay, and just telling us 1 is better than 2. Okay, we can optimize an industrial process. With really few iterations, if you do design of experiment here, we thought the level, a full factorial will be like 300 experiments. Instead, we can do in 20. Okay, so just to summarize, so how can we address data scarcity? So maybe incorporate feedback, okay, from humans, okay? Sometimes this feedback is quality, is very cheap to collect, and it gives us a lot of information. So we want to keep humans in the loop until we have enough data, maybe to automatize more. And what we can do, we can apply this idea to no, any application, because it's application independent and context-free. Okay, so if you want to know more about the models we use, there is also a software library. You can look at this. So thank you.